Okay, let's first of all start by talking a little bit, excuse me, a little bit of review over covalent bonding. First of all, what is covalent bonding? Covalent bonding, sharing of electron pairs, and we discussed different types of covalent bonds. What was one type of a covalent bond we discussed? Huh? I couldn't hear you. I'm getting old. Okay, we have polar covalent bonds and non-polar covalent bonds. How did we determine whether something was a polar covalent bond or a non-polar covalent bond? Ethan? The difference in electronegativity. And remember, we had electronegativity rules, okay, and certain ranges of numbers. And where do we find those numbers? On our periodic table. Excellent. Okay. Now, of these covalent bonds, we talked about double covalent bonds, single covalent bonds, and triple covalent bonds. What's the difference? What's the difference between a double, a triple, and a single? Lauren, what do you think? Has what? Okay. Okay. So she's talking about here about double and triple compared to single. It's the amount of electrons that are being shared. Okay? How many are shared in a single bond? One pair, right? So how many are in a pair? 2 electrons. What about a double bond? How many in a double bond? 2 pair, right, which is 4 total. How many in a triple bond? 3 pair, which is 6 total. Single, double, triple bond. All right, today we are going to get into something that we call Lewis structures. Lewis structures. So I'm going to start off with explaining, coming up here on the board, what is a Lewis structure? What is a Lewis structure? A Lewis structure is a dot structure that represents shared electron pair or lone pair of electrons. The shared pair are represented by either dots or lines. We called them dashes yesterday or 2 days ago. Dots, lines, or dashes. And we are only representing the valence electrons. Once again, what were the valence electrons? What is valence? Graham, what do you think? The outermost electrons. So we're only dealing with the outermost electrons when we're talking about Lewis structures. These are named after a gentleman, Gilbert Lewis. Okay? And what Gilbert Lewis, his claim to fame is he discovered the covalent bond. So a little bit of chem trivia there. Who discovered the covalent bond? Gilbert Lewis. So he's going to have these dot structures representing these covalent bonds. And he said, you know what, I might as well just call them Lewis structures. Now, we have some rules that need to be followed when we are making our Lewis dot structures. And the very first rule is we need to gather the information. So the first step in drawing these Lewis dot structures are to gather the information. You need to draw the dot notations for each atom that's involved in the compound. When placing valence electrons around an atom, place one electron on each side before pairing any electrons. Now, this is, let me get the next part up here first on the rule, okay? This is going to see, what you're going to see with these Lewis structures is it's going to be a little bit different than how we described our dot notation. Okay, doing the Lewis structure is going to be a little bit different than the dot notation. Let's just talk first of all about carbon. Let's talk about carbon. If we were going to draw the dot notation for carbon, we would draw it like this. Correct? That is how we would draw our dot notation for carbon. We're going to adjust that a little bit, okay? We're going to adjust that a little bit because we're going to place one electron on each side before pairing. So when we draw carbon, we're going to think of carbon like this. With one electron on each side of the atom. Why are we going to do that? The whole reason why we do that, think about covalent bonding. We stated a little bit earlier that covalent bonding is the sharing of electrons, right? The sharing of electrons. Well, when I look at this one, the way that's set up there, we can only share a couple of electrons, right? Because we've got a whole bunch of blank area right here. But when I set up this one, I've got, well, that looks like a B, not a box. When we set up that one, I've got 4 possible bonding sites right there, don't I, with carbon. So we're going to see that carbon is going to act more like that with these 4 bonding sites than it will over here. So we need to think of it like that. Okay, think of it like that. So we determine the number of electrons that are involved. Next, we need to arrange the atoms. We need to arrange the atoms to show how they bond. Well, go ahead and copy these down and then we'll talk about them. We need to arrange the Lewis structure to show how the atoms bond in the molecule. Halogens and hydrogen. Halogens and hydrogen atoms often bind only to one other atom. So they are usually at the end of the molecule or on the outside, so to speak. Remember that these halogens and hydrogen only have one electron missing from filling their outermost octet. So they're only going to want to bond with one other atom. If we have carbon, it is often placed in the center of the molecule. So usually, carbon is in the center if it is there. With the exception of carbon, the atom that goes into the center is often the lowest electronegative atom. So if you don't have carbon, you need to look at the electronegativities unless it's a halogen or hydrogen. Okay? And I think these will make more sense once we start working some examples. Okay, so if you're saying I don't get what that means yet, that's okay. Just hang tight till we get all the rules. Okay? Rule number 3 tells us that we need to distribute the electron dots so that each atom, except for hydrogen, beryllium, and boron, satisfy the octet rule. We're going to talk a little bit later on about these exceptions, but the reason hydrogen, beryllium, and boron are exceptions to the octet rule is because they're not going to require a full octet to achieve their stability. Okay? We know that hydrogen's the easiest one to look at because it achieves its stability with only 2 electrons. Okay, that fills up its full outermost shell. So those are going to be a little bit different because they don't satisfy the octet rule. But we distribute the dots around the atoms so that the octet rule is obeyed. We then will draw the bonds. We change the dots into dashes. Change the dots into dashes where we have covalent bonding. Okay? I guess that could be a little more clear. Change each pair of dots that represent, I guess it says a shared pair. Okay? So the shared pairs, the covalent bonds, we change the dots into dashes. We do not change the dots into the dashes with unshared pair. Only the shared pair of electrons do we change to dashes. Finally, we need to verify the structure. The final step is to verify the structure. You need to count the number of electrons surrounding each atom to ensure that each atom is satisfying the octet rule. Also, you need to check to make sure that you have not added any new electrons to your structure. Okay? So, remember when we drew this in our notes? This is going to be a tremendous help to you when you are drawing these Lewis dot structures, because this shows you how the majority of the nonmetals want to bond and the possibilities of their bonding. Okay? So, for instance, let's say that I have oxygen as my central atom. Okay? If oxygen is my central atom, I can know that oxygen can double bond or it can single bond. So I don't even have to worry about trying to make a triple bond with oxygen because it ain't going to happen. All right? Look at nitrogen here. It can make double bonds, it can make single bonds, it can make triple bonds. Same with phosphorus. Carbon is probably the one that is the jack of all trades because it has a bunch of different bonding options. So let's go ahead and just check out something. Here's my compound, carbon tetrachloride. Okay, carbon tetrachloride. I can look here and see, I haven't done it yet. Maybe we should do it, but let's look. Let's look at if we would calculate, because I know that this is going to covalently bond, because why do I know it's covalently bonding and not ionically bonding? Who can answer that question for me? Why do I know that this is going to covalently bond and not ionically bond? Ethan, you got it? Huh? Yeah, they're both nonmetals. In order to have an ionic bond, you need to have a metal and a nonmetal. These are both nonmetals. So, when I look at this and I do my electronegativities, I come up with a difference of 0.61. Okay? Chlorine is a 3.16, 2.55 for carbon. So that would confirm. But I'm just looking at these, I can say, okay, here's a nonmetal, here's a nonmetal. This is going to covalently bond. All right? So the first thing I would do, and it tells me, is to survey what we have. Survey what we have. Well, I have a carbon, and I'm going to make its dot structure like I showed you with one on each side. And I also have 4 chlorines. And I know that the dot structure for chlorine is dealing with 7 valence electrons. Now, some things about this that I should recognize right away. Some things I should recognize right away. Number one, I have carbon, right? When I have carbon, it almost always is the central atom, the one I put in the middle. The second thing, I have chlorine. Is chlorine ever a middle item? No, it wants to be on the outside because it only has one open bonding site. So I'm going to put my carbon in the middle. So I have carbon right here. And I know that based on that chart that I was given, that I could have carbon doing this, double bonding, triple bonding, a double bond with 2 singles, or 4 single bonds, right? Those are the 4 options on your chart that you have, correct? So I look at this and I say, okay, how is this going to fit together the best? Well, if I'm looking at this one, this would be carbon. If I'm looking right here, carbon would be double bonded to 2 other items. Is that going to fit good with 4 chlorines? No. What about this one? A triple bond with another one. That's not going to fit good either. The best fit for this particular one is going to be which one? The bottom one here. All single bonds. So what I'm going to do is I am going to put a single bond with chlorine. I know that chlorine has 7 valence electrons, right? So the blue ones are the chlorine's valence electrons. The green one is the carbon's. What I'm going to do is I'm going to bond all 4 of my chlorines like that. So now that I've got all of my chlorines bonded, single bonded onto that carbon, I go back and look and say, okay, do I have everything obeying the octet rule? I need to check with every single one of these. So, is this chlorine obeying the octet rule? Yes, it has 7 of its own with 1 carbon. What about this one? What about this one? What about this one? Yes, all of the chlorines are now. Are all, or all, is the carbon obeying the octet rule? Is the carbon obeying the octet rule? Yeah. So everything here is jiving well with the octet rule. So we have built our first Lewis dot structure. Now what I'm going to do is I'm going to replace the bonds with dashes. So you're going to see that I can write it like this. Do I need to include the unshared pair of electrons? I could. I could include those, but I don't have to. Okay, I could include those, but I do not have to. So that is my Lewis structure for carbon tetrachloride. We've got our first one built. And I think my next slide just shows you. Yep. Here's something we should be familiar with. CO2. Carbon dioxide. We exhale it all the time. Carbon dioxide. So I'm looking up here and I say, okay, I've got this guy carbon again, so he's going to want to be in the middle. Carbon's going to want to be in the middle. And I've got 2 oxygens. So I need to figure out how these guys are going to come together. Once again, I think about my carbons. And then I look over and I say, oh, let's think about my oxygen too. So my carbons are as so from our chart, right? My oxygens are as so. Now let's just say that I choose this oxygen, okay, this oxygen to single bond. Now, if I single bond oxygens, I can either do it right here or I can do it right here, correct? So let's say I chose to single bond oxygen to carbon. Well, I'm going to put them right here. And I'm going to put the other one right here. Now remember that oxygen only has how many valence electrons? 6, right? So I can't add any more electrons on there. So when I'm looking at this one right here, I see that I have 1, 2, 3, 4, 5, 6 with the 1 carbon. Now, I've single bonded both of those oxygens on there. Do they obey the octet rule? No. Does carbon obey the octet rule? No. Neither one of those obey the octet rule. So those aren't going to work. Now, if I look at the next one, if I look at a different one, right here, this one, is this one going to work for carbon here and oxygen? Think about it. Will that work for carbon and oxygen? Could I double bond here? Does oxygen like to double bond with carbon? I could double bond there, but how am I going to fill two things here? Do I have three things that I can bond to this? No. So that's not going to work either. Because if I double bond with two singles on carbon, I'm going to need to have at least three other atoms. And I only have two. So we just said that oxygen likes to double bond. So could I double bond an oxygen on one side and then double bond one on the other? Yeah. Okay, yeah. So that's what we're going to see. So we're going to say right here that this one will fit with oxygen double bonding. So as I'm drawing these out, I am going to adjust my dots to make double bonds. I know that when I double bond, how many electrons are shared? How many electrons are shared in a double bond? 4. So I'm going to put 2 from carbon and 2 from oxygen on each one of those. That's how I got the 4 of them right there. Oxygen's going to share 2 of his. Carbon's going to share 2 of his. Now, if I look, counting the shared ones, 1, 2, 3, 4, 5, 6, 7, 8. Does that oxygen obey the octet rule? Yes. Counting the shared ones right here. 4 and 4 is 8. So does carbon okay? Yes. Now right here, 4, 5, 6, 7, 8. Is oxygen okay? Yes. So we're obeying the octet rule with all of those. How am I going to draw this out? Once again, I'm just going to use the dashes. So I'm going to have carbon double bonded with oxygen, double bonded with oxygen. There I have my Lewis structure. There I have my Lewis structure. Now, let's check out. I think I got one more. There's my actual vision. And you'll learn, okay, they're representing why they're putting these dots here and here. Okay? You'll understand that in a bit when we talk about valence shell electron pair repulsion theories. I told you the VSEPR. I mentioned VSEPR in our notes the other day. That has to deal with molecular geometry. We'll learn that a little bit later. The final one that I am going to work is going to be NH3. Now, NH3 is something that is important because you need to memorize what NH3 is. It is ammonia. Okay, that is a common name that we call NH3, ammonia. Now, when we draw these two dot structures, I know that nitrogen has 5 valence electrons. So there is my dot structure for nitrogen. Hydrogen has 1 valence electron, right? I have 3 hydrogens. If you look at your chart Hydrogen only wants to single bond, right? Go ahead and take a break. We'll continue with a couple more right after break. Now, looking at this, okay, looking at this as I'm dealing with nitrogen, okay, as I'm dealing with nitrogen, I have how many choices? 3. One of them is this, right? The second one is this. And the third one is, whoa, look at that end. Wow. That end was kind of shaky. The third one is going to be this. Right? Now, you might say, how do we do this? How do we do this? I know nitrogen's going to be in the middle. Why? Why is nitrogen in the middle? We can look at electronegativity, but the main reason that nitrogen's in the middle is hydrogen doesn't want to be in the middle. Hydrogen's never in the middle. Okay, halogens are never in the middle. Okay, nitrogen's going to be in the middle for that reason, that hydrogen doesn't want to be in the middle. Now, as I look at this, rule out what you know is not going to happen. Are we going to have a triple bond? No, we're not. Are we going to have a double bond with a single bond? No, because hydrogen's not going to double bond. Okay? So are we going to have a single bond? Yes. So we're going to have nitrogen in the middle, and we're going to single bond the hydrogens. Now, as I take a peek here, and folks, when I'm making these Lewis structures, I love to use different colors because it helps me understand what electrons go with what element. Okay, I love to use different colors. It's probably the OCD in me. I don't know. But as I look at nitrogen there, is nitrogen satisfied with the octet rule? Yes. Is hydrogen satisfied with the octet rule? No, it is not, because they are not an octet. But remember, hydrogen is one of our exceptions. Hydrogen doesn't want to achieve an octet. It only needs 2 electrons to fill its outermost energy level. So, do I have an adequate dot notation there? Yes, I do. So if I'm going to draw this using my dashes, I'm going to draw nitrogen bonded to 3 hydrogens. Nitrogen bonded to 3 hydrogens.